Okay, so I think I'd like to take a look at just sort of a recap of the first derivative analysis. So first let's talk about the procedure. The first thing we would need to do is we have to compute the first derivative if that's not already known. Uh, the second is we need to find the critical values. Find the critical values. Now that would include the two types. We would have type 1. Type 1 is where the derivative is equal to 0. Type 2 is where the derivative does not exist. Remember that there are certain types of functions for which there are no type 2. There will not be any type 2 critical values for polynomials, for any function involving only sine, and for any function involving only cosine. So if the function is polynomial, if it's a sine function, if it's a cosine function, or if it's any combination of those three, then the function, you know going in, you know at the start that there are no type 2 critical values. Any other function, you would need to check to try to find the type 2 critical values. Now, there's no guarantee for any given function that either of these are going to exist, but you need to be able to account for them and search to find them if they do exist. Once you find the critical values, that cuts the number line. So that cuts the number line into pieces. Then, once you've cut the number line, you select representatives. You select a representative value from each of those regions. And evaluate the first derivative. This is the first derivative analysis. This is the key usage of the first derivative. Evaluate the first derivative at the representative values. Not the cut values, at the representative values. All we need to determine is whether the function is increasing or decreasing. All you need to do is to determine if the function is increasing or decreasing on the intervals. If, for a particular subinterval, if the first derivative is less than 0, if it's a negative number, then the function is decreasing on that interval. If the first derivative is greater than 0, if it's positive, then the function itself is increasing on that interval. If it's easier to actually compute the number, simply compute the number and determine whether that number is greater than 0 or less than 0. In some cases, it's easier to simply determine whether the value is positive or negative. We saw that when we worked with some derivatives that were fractions. All you need to do is determine the signum, the positive, negative of all the various factors in the fraction. Use the rules for multiplying and dividing a fraction to determine if the function is positive or negative. And then once you determine the intervals of increase and decrease, then we can also determine if there are any relative extrema. So, if this is a number and this is a number, and we've selected a representative from this region, suppose we've selected the representative value m, if we find out that the function is increasing on that interval because f prime of m is a positive number, and suppose we choose a value for here, n, And suppose we find the derivative is negative, f prime of n is negative, then we know the function is decreasing. Now, if it changes from increasing to decreasing, then there is a potential relative maximum at x equals a. You would take the function, the value of a, plug this into the original function, and that determines whether, if that value does exist, then there is a relative maximum at that value. If you plug a into the original function and you do not get a solution, that means there is no relative maximum at that value. Now, suppose we choose a value over here, let's call it p, and we find out that the function is increasing in that interval. Now there is a potential minimum at that point. Compute f, the original function, at b. If that value exists, then there is a relative minimum at that point. If that value does not exist, then there is no relative minimum at that point. So in order to have a relative max or relative min from this first derivative analysis, there must be a change of increasing and decreasing. Now let's suppose there's another interval out here, and suppose in that interval it continues to increase. Then this point, at that point, let's call it c, at that point, then there is neither a relative max or a relative min. There is no extremum at that point because the function has not changed from increasing to decreasing or vice versa. The relative extrema potentially exist only if it changes from increasing to decreasing or vice versa. If there is no change, there is no relative extremum. This is the procedure to follow to do the first derivative analysis.